All right. Let's talk about what a relation is, first of all. Real simple. A relation is some sort of set of ordered pairs, right? Just like this. Don't I have a set right there? And if I put some ordered pairs in there, 1, 3, 2, 5, if my pen would want to work, and you don't have to write this down, and 3, 6, isn't this some set of ordered pairs right there? That's called a relation. Okay, mathematics, lots of crazy words today. Relation is one of them. It's just a set of ordered pairs. And it could be an equation. It would be the set of all ordered pairs that make the equation true. So a relation can be classified into discrete, which means dots. Let's put that underneath the word there. Discrete means dots. Or continuous relations, which means like you filled in the dots. You connected the dots with your line. Example, see this first discrete relation? Did they connect the dots at all? No. It's just a discrete situation. You do not connect the dots. It goes from this dot to that dot to this dot. The graph looks like a bunch of dots. It's discrete. The continuous relation, solid line all the way through, nice and continuous. Okay? So, while we're kind of doing that talk, let's think of some situations. Can you think of a situation where a graph would be represented by discrete relation, meaning only dots? Well, since we're kind of in a crunch for time, what do you think about this? The number of bags of chips you could purchase versus how much it costs. That is discrete. I'll let you write that down, so pause the video and get that written down. Why would the number of bags of chips purchased versus the cost end up being nothing but dots on the graph instead of connecting them together? Any ideas? It's all about this. How many bags of chips can you purchase? Can you buy 0? Can you buy 1? 2? 3? Can you buy 1.5? You either buy a bag of chips or you don't buy a bag of chips. So these numbers, which is kind of called your domain, if you will, not every real number in the world works. Wouldn't it be only the whole numbers? 0, 1, 2. So you could plot, this would be 0 bag of chips at $0, 1 bag of chip at $1, 2 bags of chips for $2, right? You can't connect the dots together because you can't buy 1.5 bags of chips. You with me on that? So that's a discrete situation. Now the next one says, can you think of a situation where the graph would be represented as a continuous relation, to where you could have that filled in all the way? And simple thing is usually if the thing on the x-axis is time, right? Because does time ever stop? No. So what do you think about this? You've done this many times. The height of a rocket versus time. The height of a rocket versus time. So here'd be like a rough sketch of it. You'd only use the first quadrant, but wouldn't the rocket like start here and then go boo and then hit the ground? Isn't that a nice continuous graph right there to where there's no holes in the middle? The rocket is in the air and it stays in the air and it stays in the air and it stays in the air and then it finally hits the ground. That's a continuous situation because it can be at the air at 0 seconds or at 1 second or at 2 seconds, but can't it also be in the air at a half a second and a quarter of a second and all that extra stuff in there? So the time axis means that every real number from here to here is included. We're kind of cool with discrete versus continuous. All right, let's move on. A function. This definition, either highlight it or put a box around it. We will talk so much about functions. Is a relation in which each element of the domain is paired exactly with one element in the range. Each element in the domain is paired with one element in the range. Let's put a little helpers above this. The domain is our x values, and the range is our y values. The domain is the set of numbers that work for x, right? And the range is the set of numbers that work for y. So as you can see here, here's our first example. This is a relation. Why? Because it is a set of ordered pairs. Are you down with that? This is a relation. It is some set of ordered pairs. Cool? Let's see if it's a function or not. The easiest way when given a relation is to make a mapping of these. So let's make this cool little mapping. Let's make this. Let's put a domain and then put a nice little oval. Just freehand it. and make a range and make this little oval right here. So I'll let you pause the video and draw that real quick. And then let's put our domain in there. The domain is a set of x values, but we don't list anything more than once. This is kind of like a nice little room that you can go in. And if I said, hey, Mr. Fonenstiel, it's time for you to go in this room. Cool, I'm in the room, Mr. P. Then I say, hey, Mr. P, time to go in the room again. Well, wait a minute. I'm already in the room, right? I can't go in the room twice. So if you see the same number listed for x values more than once, it can't be in there more than once. It's already in the room. So what I mean by that is let's just start from left to right. It doesn't matter what order these are in. I just go what they listed. Isn't 1 an x value? So 1's in the domain. Cool. Isn't 2 an x value? So 2's in the domain. 6 is an x value. 6 is in the domain. 1 is an x value. 1 is in the domain. Is it already in there, though? It can't go in the room twice. Once 1's in the room, you don't put another 1 down here. Does that make sense with you? 1 was already in the domain. Sound cool? Now, let's list our range. Range, just the order they give them. 5 is in the range. 7 is in the range because these are our y values. Notice how I'm putting them straight down also. I'm not just putting them wherever I want to. Negative 4 is in there. And negative 2. Did you see there were no repeaters, if you will, in the range? Sound cool? And then to make a mapping, we just straight put these cool little arrows according to what their ordered pairs were. So if we do 1, what did 1 like match up with in the ordered pair? Doesn't 1 go with 5? So it's like 1 maps to 5. Put that cool little arrow right there. Let's make it green. 1 maps to 5. You just freehand it, but make it an arrow. Cool? And what does 2 map to? 2 maps to 7. 6 maps to negative 4, correct? And 1 maps to negative 2. Are you cool with just the mapping? And I will ask you to do this on your homework. Anytime they give you a relation and they're asking you all these questions, make a mapping of it, okay? Just a little freehand, doesn't have to be the prettiest thing, not the biggest thing in the world either. But from the mapping, you can tell immediately if this is a function or not a function. Because according to the rules, a function says this: every element of the domain is paired with exactly one element in the range. And as you can see, do you see the old number 1 right here? Doesn't it map to 5 and it also maps to negative 2? That's against the rules. You can only have 1 arrow coming off your domain, guys. Doesn't this dude have 2 arrows coming off of it? So is this a function, yes or no? No, and here's the reason. It's very specific. The element 1 in the domain. Please write this down. No, this is not a function. The element 1 in the domain maps to more than 1 element in the range. That is the specific reason why that was not a function. Because didn't the guy number 1 in the domain go to too many things? So the element 1 in the domain maps to more than 1 element in the range. That is against the rules for it to be a function. Feeling okay so far? Number 2, or the next part, make a mapping of it first. So please pause the video and let's make a mapping of it. Are we cool with what the mapping should look like? So now you can tell if it's a function or not. You really care about over here. Aren't there just arrows coming off of, 1 arrow coming off of each element in the domain? So is this a function, yes or no? Yes. Why? You just basically state the definition again. Every element in the domain maps to 1 element in the range. Yes. Every element in the domain maps to 1 element in the range. Those were relations which were ordered pairs. We made a mapping. If you've got a graph of the function, notice the key word is graph, you can use what's called the vertical line test. We always call it the VLT because it stands for vertical line test, to see if that's a function or not. So just watch this bad boy here. You see this? Let me highlight it so it's a little easier to see. See that red parabola right there? Let me do some vertical lines through it. Line, of course. There's the one they gave us. How many places does that vertical line touch the graph? 1. That's okay. But if you can find a vertical line that goes through it in more than 1 spot, then it's not a function. So One is not enough. You got to test a ton of them. It's like, how many places did that vertical line go through there? One. How many places did that vertical line go through there? Would it be possible for me to make a vertical line and go through this particular parabola in more than one spot? Is it even possible? No. So is this the function? Yes, it is, because the graph passes the vertical line test. Okay? Now check out this graph. See that dude right there? Here's the vertical line. How many places did that go through there? More than one, correct? Two exactly, but it doesn't matter how many times. It's more than one, correct? Is that a function? Yes or no? Can't be, because the graph fails the vertical line test. Check it out, though. I can find a spot right there. Didn't that vertical line, if I'd have made it a little more vertical, go through it exactly one spot? It doesn't matter if you can find a spot. It's can you find a situation to where the vertical line goes through there? So let's test some more. That's not enough. You don't have this on your practice sheet, but let's try. Sorry. Okay. So is this a function? Well, let's try the vertical line test. Why am I even able to use the vertical line test? Because these are graphs. Sound okay? It's not a relation. These are graphs. What do you think? How many spots? One. How many spots if my pen would work? One. How many spots? Is it possible for me to have a vertical line go through there in more than one spot? Is this a function? Yes. Reason? Don't say it passes the VLT. The graph passes the VLT. Sound all right? What about this guy? Can I find a vertical line that goes through there more than once? Well, that vertical line right there only went through it in one spot. Correct? What about right there? More than once. Is that a function? No. The graph fails the VLT. What about this guy? That's a line, right? Isn't that just a plain old line? You've graphed them for years now. Vertical line. Will it always work? So is it a function? Yes or no? Yes, because the graph passes the VLT. What about this guy? Would I be able to find a vertical line to go through this in more than one spot? So this is a function, correct? The graph passes the VLT. Boom. Is that a function? No way, right? The graph fails the VLT. Pass, 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 pass. Can I find a spot? What about right there? Did that pass the vertical line test? Looks like it went through it right here, and right here, and right here, and right here, and right here. There's an infinite amount of places where that doesn't work right there. Cool? So, is this a function? Yes or no? No. So, now that we can kind of handle what a function is, here's the thing on the next page. As I stated earlier, this is a super complicated lesson. We're going to simplify it real easy because here's the thing. We will always be talking about functions. Sound okay? We will be talking about functions, about this. One-to-one, on-to, or both. First of all, they put these in the wrong order of what you should check with. So let's kind of renumber these. This is the first thing you should check to see if a function is what we call on-to. That's step one. Then step two, we should check to see if it's one-to-one. And then finally, we check to see if it's both. And we're not going to try to overcomplicate this. We're assuming that everything given to us is either a function or not a function. So that's why we check the first thing first. Sorry, that's why we check onto first, because this checks to see if it's a function in the first place. If something is onto, it says each element of the range also corresponds to an element of the domain, but blah, 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 blah. It says if it's graphed, it passes the what? The VLT. Isn't that the test in the first place to see if it's a function in the first place, right? If it passes the vertical line test, it is considered to be an onto function. What does that mean? That this 1 maps onto D. This 2 maps onto B. This 3 maps onto C. This 4 maps onto C. Doesn't everything in the domain have something to map onto? But it only starts one arrow coming off your domain. It can map to whatever it wants to over here, but nothing was left out. Sound okay? That's onto. The second thing you check for if it's what we call one-to-one. And to do that, you can tell real easy by the graph if it passes the HLT. Well, VLT stands for vertical line test. What is HLT? Horizontal line test. Sound okay? But one-to-one is very specific. Can you kind of see that this maps to one thing, right? And when it maps back, it only maps to one thing, right? D only maps to 1 if you go in reverse order. 2 only maps to B, and B only maps to 2, right? And 3 maps to A, and A only maps to 3. See, there's like a one-to-one correspondence. There's no double ups. You see how C, if you go backwards, would kind of map into 2 different things, right? This is 1 to 1, right? Each thing maps to one unique range, and each range maps back to one unique domain, 1 to 1. But like I said, I don't want to overcomplicate you, but you see how there's some weirdo in the range that like didn't even get mapped to in the first place? Let's not let this bother us, okay? Just realize 1 to 1. Sound all right? And then finally, it's both if it's 1 to 1 and onto, if it passes the HLT and the VLT. And do you see here what got eliminated was that like extra dude that had no one to map to? So then this only maps to that, and backwards it only maps to that. It's 1 to 1 and onto at the same time. But we don't have to worry about these weirdo situations because we're going to do this. It's got to be a function first. So number 1, boom, got to pass the VLT. Cool. Number 2, check to see if it passes the HLT, which means it's onto. Then number 3, if it passes them both, isn't it both? Right? So it's both. So here's my cool little trick to remember, because I have a hard time remembering stuff. I need to come up with stupid little acronyms. So onto starts with an O, 1 to 1 starts with an O. Here's how I did it. If the graph passes the VLT, it's onto. V is the most important thing, and onto. And since we live in a Volga German society, and we're kind of familiar with German accents, don't we want to check that first? We want to check that. If you put the V and the onto together, you get want to. We want to use the VLT first. Now, sure, right? So want to. Then the second thing you do is HLT, 1 to 1. If it passes them both, then good for us. Sound right? Then it's both 1 to 1 and onto. But it's like, which one does onto go with? It goes with vertical line test. Vertical line test, onto, meaning it's a function. Whew, complicated. Let's try some. So here's my cool little check sheet, or cheat sheet, whatever you will. Here we go. Consider these 2 graphs below. Number 1, they ask if this is a function. Well, if I got a graph, there's one way to check to see if it's a function. What should we use? The VLT. Does this brother pass the VLT? Yes or no? So is this a function? Yes or no? Yes. Reason? The graph passes the VLT. The question is this onto, which sounds a lot like vonto? To be vonto, you got to pass the VLT. Did this pass the VLT? Yes. So the answer to that is yes. Seems kind of weird, but we had to do this. We first had to figure out is it a function. Yes. How come? Because it passed the VLT. Cool. Then you have to figure out if it's onto. The rules for onto says if you pass the VLT, you're onto. So didn't we already pass the VLT? So that's a bingo on onto. Cool? All of this stuff was about vertical line test. Onto, vonto. Function, vertical line test. Cool? Next, it says, does this pass the HLT, the horizontal line test? What do you think? Absolutely not. You should draw one if it fails. Draw a horizontal line. You can sketch it for now and find your straight edge later, but on homework. If it doesn't pass it, you better show me one. Okay? If it doesn't pass it, show me. So did this pass the HLT? No. Meaning, is it 1 to 1? Yes or no? Well, 1 to 1 is about HLT. If you pass the HLT, then you're 1 to 1. Is that 1 to 1? No. Cool? Now, let's start with this problem right here. Is this a function? What do we need to use to test to see if that's a function? VLT. Does this pass the VLT? Yes. So is it a function? Yes. Why? The graph passes the VLT. Boot. Yes. The graph passes the VLT. They want to know if it's onto. Well, to be onto, you have to pass the VLT. Is this onto? Yes. If you say yes to this, you have to say yes to this. It's just like part of the rules right there. Okay? All of those go together. Does this pass the horizontal line test? Yes or no? Yes, it does. So is that 1 to 1? Yes. Which really means it is both. It's 1 to 1 and onto. Right? We will never have a situation, because we're talking about functions, where something will only be one-to-one. It has to be both for what we are trying to do, because they are functions in the first place. Cool? Next. They give us a mapping. They say state the domain and range in each relation, then determine whether each relation is a function, whether it's one-to-one, onto, both, or neither. So domain, isn't that the set of all the x values? Correct? Isn't there a finite number also? There's just 3 of them in there. So we need it as a set. 100, 200, 300. We'll not say like the set of all x's such that x is 100, 200, or 300. It's just there was only 3 numbers in this domain. Boom, boom, and boom. We do that crazy stuff when there's like an infinite number of in there. We just have to determine which ones work and which ones don't work. Range. Isn't that 50, 100, and 150? Sound okie dokie. Just the set of all the y values. We feel okay with that. If we graph that, would it be discrete or continuous? If we plotted those ordered pairs, would it be discrete or continuous? You got anything that says you're supposed to connect the dots together? Or wouldn't you just plot 3 dots? You'd plot 150, 200, 100, and 300, 150, right? This is a discrete situation. Cool? Next, circle all that apply. Is it a function? Well, we can't use the vertical line test. It's not a graph. We check the arrow test, the mapping. Is this a function? Yes or no? Yes. How come? Because every element in the domain maps to one element in the range. In our own words, coming off one arrow only. Rock and roll? Is it one-to-one? Well, we don't really check that right away. We kind of got these in backwards order. Remember how we had to renumber the steps? Isn't this the second thing, which should be the first thing we check? If it's a function, is it onto? Yes or no? It's got to be onto. So that's the next thing you move to. Then you got to check if it's one-to-one. Well, you can tell that by the arrows. Don't the ranges map back to the domains only one-to-one also? Is that cool with you? So is this one-to-one? Yes, which means it's also both. It says circle all that apply, so we circled all that applied. It was a function. It was onto because it was a function in the first place. It was one-to-one because the range is only mapped back one time also, and that means it was both. Next guy, domain. What is it as a set? Set of 3. If I can make a nicer set bracket. 3. Range, 1 and 5. Cool? Is it a function? Yes or no? Why is the answer not a function? How come this is not a function? In our own words, too many arrows coming off of this. Cool? But we got to learn the right words. The element 3 in what? Domain. What is it doing here? It's mapping to more than one element in the range. The element 3 in the domain maps to more than one element in the range. Not a function, so boom, automatic neither. Cool? Next. Domain, list it, and range on number 3. Pause the video, get that done. Domain and range. So there's our domain, and there's our range. Cool? Don't list anything more than once. 4 appeared more than once. To do this trick, I don't care if you can see it without the mapping. I'm going to make you make a mapping of this situation. So please make cool 2 little bubbles. Put a D above the domain and an R above the range, and let's make a mapping of these situations. These are major state assessment questions right here. Are we cool with that mapping right there? So is that a function, a yes or no? The answer is yes. In our own words, how you can tell without the mapping, but I still want you to make the mapping, were there any repeaters in the domain? Yes or no? There was no repeaters in the domain, so that's going to be a function. Then we jump automatically to if it's a function, we check to see if it's onto. If it's a function, is it onto? Yes, functions and ontos go together. Cool? Is this one-to-one? Meaning if you went backwards, would there only be one arrow coming off of each range guy? No, this guy violates it right here, correct? So it is not one-to-one, meaning it is not both, and it's definitely not neither because it was onto. We okay with that? Now we get interesting here because number 4 is a continuous function. It's not just a bunch of dots. Isn't it an infinite amount of dots? So domain is what the x's can be. For this particular graph, not in general, it's for this particular graph. So we will start out with the set. It's the set of all x such that. Is there like a minimum value? This is the numbers I'm looking at, right? Right here. This is the numbers I'm looking at. What's the smallest number that you could possibly see in this graph as an x value? 0, right? Isn't at this point right here, it's 0, like 7 or whatever you will. And then doesn't it keep going and keep going and keep going and keep going and keep going? And then we end up like right there, which unfortunately we're going to have to approximate. Where would you approximately feel that that is? I got to see what the scale is. Aren't these going by 0.2s? Right, so that is very close to 1.2. Like what would you call that right there? 1.09 maybe, you know? 1.19, sorry, 1.19, right? So we're going to write that as a double inequality. Set of all x such that x is smaller number, 0. Symbol points to the left. Should it count? You bet. X goes in the middle. Symbol points to the left again. It'll count. And then we'll say approximately 1.19. We kind of had to round that. That's in set notation. Correct? Off to the right. Let's put it in interval notation also. Let's put that in interval notation. We just used the brackets and the parentheses and all that stuff. How far left would this thing go? 0. Would it count? So wouldn't that be bracket 0, comma, and then approximately 1.19? And that counts also. That's that same information in interval notation. Is that cool with you for the domain on that guy? Range. Range is the y values. Isn't that high versus low right here? High versus low, the y values. Cool? What's the lowest y value you got? Oh, by the way, this is where we screw up the most. Set of all what? Y's. We don't put x because it's not domain, it's range. Set of all y's such that, what's the lowest y value that you see on here? Isn't it right here? Isn't this as low as that bad boy would go? At 0, it counted, and then y's in the middle. What's the highest that bad boy gets to? Well, I got to check my scale. Aren't they going by 2's here, right? So this number right here is 12. That's about what? What do you want to say? 11.8 would be fine. There's no exact answer, but it's got to be more than 11, less than 12, right? More than 11, less than 12. Put that in interval notation for me. The only reason we put those approximates is because we weren't sure. We had to round it, right? If you are sure, then you don't put the approximates. Is that cool with you? And now let's check it. Is it a function? Well, since it's a graph, what would you use to check to see if that was a function or not? VLT. Would that thing pass the VLT? Yeah. Boom, it's a function, meaning it is also onto right away. Is it one-to-one? What do you use on a graph to see if it's one-to-one? Horizontal line test. Does that pass the horizontal line test? So, nope. Show me. And it is not one-to-one. Just a sketch, you know. I'm cool with it being a sketch if you can sketch straight. If you can't sketch straight, use a straight edge. Okay? So we don't fill out anything else. Boom! Next guy. Hey, is this a discrete graph or a continuous graph? Discrete. Let's make our domain first. Got to look through them all. I'm just going to come to them as I see them. There's a -2. Got it. There's a 1. Got it. There's a 1. Should I put it again? Nope. And there's a 4. That's it, right? For our domain. Cool. Then our range is all the y values. No order. Doesn't really matter. People always wonder if you should put them in numerical order. That's harder than you think it is to make sure you have them all in there. Like, oh my gosh. Cool? Do I need a mapping? No, I don't, because I have a graph of the situation. So let's see. Does the graph pass the vertical line test to see if it's a function? And that's kind of weird, because you're like, whoa, dude, it's like a discrete graph in the first place. But check it out. Doesn't this guy go through the graph if I put arrows on it in just one place? Doesn't this guy go through the graph if I made it? My bad. Sorry, video people. It's got to go through one of those dots, right? Because isn't the dots just the graph in itself? Doesn't that go through there? But what do you think about this dude? Well, maybe. Does that guy go through the graph in exactly one place? You don't know. Okay. Does this thing go through the graph in more than one spot? Yes or no? That's a yes. It goes through there more than once. So is that a function? What do you think? Not a function. Cool? Meaning all bets are off. For everything else, it's plain old neither. Cool? It is, since it's not a function in the first place, we got no dice. Cool? Now, let's see if we can take our lesson from last time. See that? Do you know what that will be if we graphed it? What shape? Parabola, a cubic, a hyperbola, or what is that? That's a linear function. Can't you tell just by looking? Are all variables to the first power? There is no product of variables, and there is no variable in the denominator, correct? That's a linear function. It's in slope, intercept, form, right meow, correct? Can we graph it? Yes. What do we need on our graph before we do that? We need a scale. You can't just assume that everything is going by one. So 1, 2, 3, 4, 5, and the negatives. It's like Mickey Mouse showed up to tell you that. Oh. 1, 2, 3. You guys are like, who the heck is Mickey Mouse? Then we will graph that. What's the y-intercept? The slope. Y-intercept is 2. The slope is 3. But we need it as a fraction, right? It's been a while. 3 over 1. So can't we rise 3? 1, 2. Oh, no! I can't even rise 3. So I can't rise 3. Can I go down 3? And to the left 1. And down 3. And to the left 1. And then I'll graph it. Please use a straight edge for this. Okay? When we're just doing the test, vertical line, horizontal line, that's a freehand, you know? You down with the pound on that? That's very simple to graph. Now let's see if we can figure out the domain and range. It's a line. We're looking at the graph. Are we all okay before I move on? How far to the left will this graph go? Domain is x and y. Isn't the x-axis and the y-axis go left and right, correct? So if I drew this arrow, if I follow this graph, isn't my pen going to the left, going to the left, going to the left, going to the left, going to the left? How far to the left will my pen go if I keep following that? To negative infinity, correct? If I went to the right, how far to the right? I know it's going up also, but isn't it also going to the right? How far to the right will that thing go? To positive infinity. Were there any holes in that graph? So didn't from negative infinity to positive infinity, whoops, my bad, that's the domain, what I was talking about. From negative infinity to positive infinity work. We've already got that figured out in interval notation. Can you write that for me in set notation? What does this really mean? The solution set is what? All real numbers. But we got to write it in set notation. Every real number in the world works for x. I can put anything I want to in here, and I will get a y value back. Right? I could put a 1 in there. I could put a million in there. I could put a -2 in there. I could put a 0 in there. Wouldn't I still get a y value back every single time? I could put a pi in there. I would still get a y value back. Cool? All real numbers work. I checked left to right for domain, because that's what x's roll. Y's, isn't that up and down, correct? How low will this bad boy go? Negative infinity. How high will that go? So isn't that our range also in interval notation? And now see if you can write it correctly in set notation. So it's the set of all y's such that y is an element of the real number system. Got to use y's because it was range. Cool? Is this a function? Yes or no? Does it pass the BLT? Yes. Meaning, since it's a function, it is automatically onto. Is it 1 to 1? Why? passes the horizontal line test. So it's 1 to 1 and onto, meaning it is both. Sound okie dokie smoky. Euler's notation is what this is really called. Some people call it function notation, but the reason it's called Euler's notation because the man who invented this notation's name was Euler. Right? If I invented a notation, they'd call it Fonenstiel notation, but this is Euler's notation. The crazy f of x. So we've got it in function notation. They're saying we've got f of x equals 5x minus 1. Some function of x is going to be 5x minus 1. They're asking us this. This is the hard part. How do you read that? They're saying, what is f of negative 6 is what that says. What is the function evaluated at negative 6? And let me ask you this. In generic form, wasn't there an x in this spot right here? Wasn't there an x right there? All we have to do is a little thing called substitution. Where there was an x, we will substitute negative 6 in its place. So is there an x? Right? Meow. Is there an x? Right? Meow. And we're going to show work the correct way. Here's what we will do. F of negative 6 equals 5 times negative 6 minus 1. Do you see how where there was an x, I put a negative 6 in its place? You must also remember that we are trying to figure out basically, if you go back old school, isn't that where the y used to be? All we're trying to do is figure out what the corresponding range element is. So this guy never changes. Never changes. You can't take f times negative 6. That's not what this is saying. This is your y. So f of negative 6 comes down. Now we can simplify this over here. Isn't that nothing but numbers? What's 5 times negative 6? Negative 30 minus 1. See that? Then one more step down. F of negative 6 equals negative 31. What the heck does it mean? That the function evaluated at negative 6 would shoot out negative 31 for a y value, for your range element. This function, evaluated at the x value of negative 6, gives you a y result of negative 31, is what that's all about. If you did it the other way, that's what you'd come out with. You'd have it like this, y equals negative 30 minus 1, y equals negative 31. Didn't we just figure out what the y value was if x was negative 6? Cool? But this, we try to throw away because we want to let smart math people know that it was a function in the first place, because that has something to do with what we'll do later. So let's evaluate. They give us the function. This is a function. Can you tell me if it is a line or not? If we would graph this, would this be a linear function? Yes, it's a line. All variables to the first power. There is no product of variables. Remember, that's not a variable. That's an f of x, right? That's your y value right there. There's no product of variables, and there is no variable in the denominator. So it's going to be a line. Shouldn't it be a function, right? Won't it pass the VLT? Cool. F of 12. So let's go through it. F of 12 equals, wherever you see an x, you need to put a 12 there in parentheses. I cannot accentuate how important it is to substitute stuff into parentheses. When we have exponents on these things, it gets crazy. So f of 12 really is negative 24 plus 4, correct? F of 12 would give us, with negative 24 plus 4, negative 20. Then we just go back up and put that into blank. But we got all this room down here to do work. We'll put it into blank. Let's skip a little bit. Let's jump straight over to number 9. Okay? Number 9. We got a function. What do they want us to put in for x? They want us to put 2b in there. It's got a variable in it. That variable of b will not go away. Right? There's going to be b's in our answer. It's not like we can solve for b. They're just saying where there's an x, please put 2b in its place. So won't we get f of 2b to equal negative 2 times the quantity of 2b plus 4. All I did was where there was an x, I put a 2b in its place. Sound okay? Now, this f of 2b continues to come down. Negative 2 times 2b. We could definitely multiply those together. What's negative 2 times 2b? Negative 4b. Plus 4 comes down. Then, are these like terms? So we cannot add them together. That is our answer. F of 2b is negative 4b plus 4. Sound all right? Here's what I want to do. I want you to do, well, let's do number 10 together. g of 5. You notice not every function's name is f, right? Just like not every person's name is Dave. People have different names. Functions have different names. This function's name is g, right? This guy's name is g, so that's g of x. Cool? So where there's a x, let's put a 5 in its spot. So g of 5 will equal, in parentheses, 5 cubed minus 5 goes in parentheses. Cool? You all right with that? Now, g of 5 comes down. 5 cubed does not mean 5 times 3. It means 5 times 5 times 5. Take it times itself 3 times in a row. What is 5 cubed? 125. Then you got minus 5 coming down still, right? And finally, please finish your work. Don't just go straight up to the answer blank and put 120. Finish what you're doing, right? Get me a g of 5 equals 120 right here. Like I need to see that, and then just put the 120 back up there. Pretty simple. Agreed? Now let's get crazy and put some negative numbers in, because it really matters about these exponents. Let's talk some basics. If this was an even number, like a 2 or a 4 or a 6 or an 8, if that was an even number, and you take any negative number and raise it to an even power, like negative 2 to the 4th, doesn't that mean negative 2 times negative 2 times negative 2 times negative 2, and negative times itself 4 times in a row? Will that come out positive or negative if that was an even number? It will always come out positive. Depends on how you punch it in your calculator, though, because, boy, if you don't put parentheses around that, ain't going to come out positive. You got to punch it in correctly. What if it was an odd number? What's negative 2 times negative 2 times negative 2? 3 negatives times each other. Will it come out positive or negative? It will come out negative. Simple things, right? Simple, simple things that you should have learned in Algebra 1 that we forget every once in a while. So this is what it looks like. Minus a minus 2. What's minus a minus 2 turn out to be? Those simple things just keep eating us alive. Minus a minus is a plus. Things to even power should come out positive, and etc. Simple, simple stuff. So g of negative 2 equals, what's negative 2 to the 3rd? I'm not going to punch in negative 2 to the 3rd in my calculator, especially when it gets harder. I'm going to do this. I'm going to say, a negative cubed. What will that turn out to be, positive or negative? I figure out the sign first. No need to punch in negative 2 cubed. Now maybe I need to punch in 2 cubed and figure out what that is, but isn't that 8? But I already knew it's coming out negative because I figured out sign first with my brain, then I let the calculator do the calculating on things that get crazy. Like if that was 13 cubed, I don't know. I will punch that in, right? But I'm not going to punch in negative 13 cubed. I'm going to punch in 13 cubed and realize it had to be negative in the first place. Make it sense? Negative 6, what we get? And now I dare you to do number 12 and see if you get it right in the first place. Get that done with PAL, and let's see how well we do. Here's what you got when you substitute in. Should the 7 get cubed? Yes. It becomes a 343. Should the C get cubed? C cubed. C43, C cubed. It'll come out positive, though, correct? People are like, wait a minute. That's an odd power. Doesn't it always come out negative? No. The base was positive. A positive times a positive times a positive will still be positive, correct? Only if the base was negative will that come out negative. Then minus 7c. Are those like terms? Yes or no? No. 343 c cubed has a cubed in it. 7c only has a c in it. Sound oakley dokley? Cool.